Hello, everyone. I welcome you to my presentation. My name is Henry Mato, and I'm a PhD candidate at the School of Education, Curtin University. I'm here to share with you what we have learned in terms of how students use immersive virtual reality to explore hydrogen bonding and to build their understanding in ways that textbook illustrations and physical models cannot afford. This project is funded by the Australian Research Council and is headed by Dr. Mihe Won. As educators, we believe that chemistry occurs at three levels: the observable level, the molecular level, and the symbolic level. These three levels are interlinked. Research has shown that learners always struggle to build good conceptual understanding of chemistry because, one, it is hard to see what is happening at the molecular level, and it is even hard to think about it. Therefore, learners have difficulties in establishing meaningful links between the different levels of chemistry. Besides, most of our teaching focuses on the symbolic level. However, our research team believes that if we can design learning activities capturing all the three levels of chemistry, we can help learners build better and coherent chemistry knowledge. To do this, our research team has designed activities for learning chemistry in immersive VR, in immersive virtual reality, which I will be calling IVR. What is IVR? It is a form of visualization technology. It teleports learners to a new world, which can be a new place or the molecular world, by shutting down the physical reality totally. In this way, the learner can observe, can explore, can interact with complex molecules in 3 dimensions, as well as collaborating with others in a shared space. However, our survey of literature has shown that there is a lack of studies systematically exploring how immersive virtual reality can support students' conceptual understanding of chemistry. For this study, we explored how immersive VR can support students' learning of intermolecular forces in the context of snowflakes. We chose intermolecular forces because the chemical and physical properties of substances that we see or that we experience depend on the nature of the intermolecular forces in these substances. However, research has shown that learners have difficulties understanding the nature of intermolecular forces, especially when it comes to complex molecular systems. This is because when the molecules are many or the molecules are big, complicated, learners require the skill to visualize molecules and their interactions in 3 dimensions rather than in 2 dimensions. So for this study, the specific research questions were: what is the level of students' conceptual understanding of intermolecular forces in snowflakes after the collaborative immersive learning experience? 2, how do students of different prior knowledge levels use the immersive learning experience to improve their conceptual understanding of intermolecular forces in snowflakes? In this study, we recruited 70 university chemistry major students who were in their 1st or 2nd years of study. All these students had done high school chemistry, and therefore we expected them to have basic ideas about hydrogen bonding in water. We paired these students and explicitly asked them to work together to discuss the ideas with one another throughout the activity. The procedure included a pre-test, an IVR session, and a post-test. And the whole session took about 1.5 hours for each pair of students. In the pretest, we asked learners about their understanding of the properties of a water molecule and hydrogen bonding. In addition, we asked learners to draw diagrams to show how many water molecules would interact with a single water molecule. We also gave learners pictures of snowflakes and asked them to use the concept of hydrogen bonding to explain the shape of snowflakes. After the IVR session, we asked learners to improve their drawings and also asked them to explain the shape of snowflakes again. To analyze students' conceptual understanding, we compared their drawings before and after the IVR session, as well as content analysis of their verbal responses to the conceptual questions that we asked them. In the IVR task, first we gave learners different snowflakes and asked them to explain the shape of snowflakes. Then learners were asked to explore the nature of hydrogen bond interactions between two water molecules, focusing on the distance and changing distance and angles and how it affected the interaction. Learners were then given a number of water molecules and asked to construct the basic tetrahedral unit using the water molecules provided. In the next step, learners were given clusters of water molecules and asked to connect the clusters using hydrogen bonds to create a single layer of water molecules. Then, learners were asked to stack multiple layers of water molecules together to create a big lattice structure, and to use this lattice structure to explain the shape of snowflakes. We use the students' pre-test diagrams to evaluate their prior understanding and to group them accordingly. The grouping was based on the representation of a water molecule and how the learners represented a hydrogen bond and the maximum number of hydrogen bonds created for each water molecule in the drawing. The low prior knowledge students struggled with basic concepts such as the structure of the water molecule. For example, some students were drawing double bonds between hydrogen and oxygen atoms in a single water molecule. The intermediate prior knowledge group had a good understanding of why water molecules would attract one another. However, they struggled with the orientation of water molecules around the central one. The high prior knowledge students had a good understanding of why and how a hydrogen bond formed. However, all the three groups had something in common. Most of the diagrams were flat and were showing interactions in 2 dimensions, and there were no indicators of molecules interacting in 3 dimensions. In the next slides, I'm going to share with you what we have found in terms of the students' conceptual understanding. Before IVR, we asked the learners to explain the shape of snowflakes. They always gave similar responses, irrespective of the prior knowledge level. The students' explanation suggested that a snowflake had one molecule at the center, and to this, other water molecules kept adding, leading to growth in 2 dimensions. However, after IVR, many students explained that molecules were interacting in 3 dimensions rather than in 2 dimensions. Based on the changes made in the diagrams and the explanations, the intermediate prior knowledge students seem to benefit more from the IVR intervention compared to the other groups. The high prior knowledge students always provided more comprehensive explanations. In the next few slides, I'm going to share with you how each group, based on the prior knowledge level, how each group progressed in conceptual understanding. As noted earlier, students in the high prior knowledge group had a good understanding of hydrogen bonding in water molecules, but most of their drawings were flat and did not show indicators that molecules were in 3 dimensions. After IVR, 24 of the students in this category either included indicators of the interactions in 3D in their drawings or mentioned this verbally. In terms of explaining the shape of snowflakes, before VR, 17 of the 28 students said that snowflakes were growing by molecules adding onto each other in 2 dimensions. However, after IVR, 26 of the 28 students highlighted that the 6-fold symmetry in snowflakes was because of the hexagonal patterns at molecular level. The intermediate prior knowledge group, initially they had issues, they had challenges in orienting water molecules around a central one, even though they knew that water molecules would attract based on partially positive and partially negative regions. After IVR, 30 out of 32 students in this group made positive changes in terms of the number and orientation of hydrogen bonds or water molecules around a central water molecule. Also, 28 of the 32 students in this category either mentioned that molecules were interacting in 3 dimensions or showed it in their drawings after IVR, compared to the 11 before IVR. In terms of explaining the shape of snowflakes, 18 out of 32 students in this category explain the shape of snowflakes in terms of the hexagonal patterns at molecular level after IVR, compared to 2 who explained in this way before VR. The low prior knowledge group made changes to their drawings, but the students seem to retain most of their initial understanding of interactions among the water molecules. For example, diagrams still showed hydrogen atoms attracted to hydrogen atoms in different molecules, hydrogen, hydrogen, or oxygen atoms being attracted to oxygen atoms. Also, only 3 students mentioned that molecules are interacting in 3 dimensions, and none of them showed it in their diagrams. In terms of explaining the shape of snowflakes, 6 out of the 10 students in this category mentioned hexagonal patterns at molecular level, but when prompted further, they could not explain how these patterns were created. From these findings, it was clear that students of different prior knowledge levels benefited differently from the IVR experience. Why was this the case? We used the immersive learning experience framework to investigate why such differences occurred in students' learning. In terms of the sensory immersive learning experience component, students of high and intermediate prior knowledge used visual cues provided, such as the changing thickness and color of the bond, to build their conceptual understanding. For example, when the molecules were in an optimal position in terms of distance and angle, the hydrogen bond between the two was depicted as a thick green bond. And when the angle or orientation was slightly off, it changed color. Students in high and intermediate prior knowledge groups use these changes to anchor their discussion. For example, well, when like it's on an angle, like it's not lined up straight on with the hydrogen, it's weaker. And when you get closer, it gets weaker. The transcript shows that the students were discussing the visual cues in relation to the strength of the hydrogen bond. On the other hand, low prior knowledge students did not use these cues effectively. They simply mechanically completed the task. We also did not have a way of showing attraction or repulsion among the water molecules. There was no signal. This made it hard for students of low prior knowledge students to create hydrogen bonds. Some simply stacked molecules, while others simply had one water molecule in the center and randomly put other water molecules around it without creating the bonds. So even though students had access to the same visual cues and same 3D molecules, they used them differently. The actional immersive learning component involved learners engaging in embodied actions with their bodies, such as rotating molecules, walking around, or lowering their bodies to change their perspectives. We observed that when learners engage their bodies more, they seem to benefit more. On average, learners of high and intermediate prior knowledge spent more time exploring the 3D molecules compared to the low prior knowledge group. Also, the high and intermediate prior knowledge groups walked around more and lowered their bodies more to change perspectives compared to the low prior knowledge group. In terms of the social learning component, initially we gave explicit instructions to the learners to work collaboratively and to share their ideas throughout the task. We observed that learners of high and intermediate prior knowledge made effective use of these social interactions, asking each other conceptual questions and exchanging turns while interacting with the molecules to get more ideas. For example, when exploring the 3D lattice in relation to the shape of snowflakes, high and intermediate prior knowledge students always ask questions like, why are they all flat? If water molecules keep adding onto this, why don't the snowflakes become thick? So the students went beyond what they were saying and thought about the other features of a snowflake. Snowflake is flat. Why? What creates the difference? On the other hand, learners of low prior knowledge rarely deeply engage each other in conceptual questions to build their understanding. So by interacting differently with different components of immersive learning experience, learners build different levels of knowledge depending on their prior knowledge. So in conclusion, we find that from these preliminary findings, the collaborative IVR experience helped learners to improve their conceptual understanding through embodied actions and social interactions. However, since learners of different prior knowledge levels benefit differentially, IVR should be complemented with relevant previous activities to equip learners with the basic concepts needed for them to make sense of the IVR activity. In this way, when we combine relevant pedagogy with the technological affordances of IVR, we can use IVR to support chemistry learning in ways that models and textbook illustrations cannot afford. These are the references used in the presentation. Thank you for your attention.